Welcome everyone to another RSE seminar and exemplifying the fact that we do software, not IT. We are now good to go. So this week we've got Simon, who's going to be talking about Fortran77. Yay! No. And as promised, has come in costume for Halloween. So yes, please do.
Yes, thanks very much, Jack. Title of the talk, Fortran77, C with none of the safeguards, which was a title I came up with quite on the fly, so the talk may not entirely reflect that, but hopefully I will illustrate some of the similarities between C and some of the fun things about Fortran77. And can I advance? I can, right, no. So why are we going to talk about Fortran? Why am I going to talk about Fortran? And thanks everybody for coming in costume as well. That's nice to see you all in costume. Just amazing. So why are we going to talk about Fortran? Well, firstly, it's always funny to laugh at old languages. You know, things were done differently then. Decisions perhaps were made on the basis of necessity, which these days we would find amusing or just peculiar. So, you know, we can have a bit of a giggle. We can laugh at the old and dated. Hopefully a bit of a laugh. It's fun. It is actually genuinely, I think, a fun language still to play with because it has very few checks and balances. You can absolutely let rip in Fortran77. It's a similar idea to C. If you want to just go crazy in C, you can, and the compiler, the runtime are really not going to stop you or get in your way. None of this, you know, boring, oh, you've overflowed your array or anything like that. It's just absolute chaos. And more seriously, Fortran77 is out there. There's a lot of it still out there. And it's out there in libraries, in existing code bases where the researchers are quite happily working away, maybe even writing new code, but they're not writing new code in new languages. They're writing it in the languages they know. So until those people retire or move on, they're going to keep generating that code. And then you have these gigantic code bases that, you know, who's going to port it? Researchers really don't like porting code. They're happy to sit on it. I know many code bases in Fortran77, pure F77. Another way you might see F77 is disguised, where someone has ported it to modern Fortran, but basically done the bare minimum to get it into modern Fortran, and it will therefore look very, you'll be able to identify it very easily as it was Fortran77, and I'll try and show you some of those as well. So if we're going to wait for it to die out, we could be in the same boat as the people waiting for COBOL to die out, the banking industry. You know, it's just investment of time, although I believe COBOL is finally going away. So quickly, what is Fortran77? Well, Fortrans I to IV were, of course, invented by the Roman Empire, you can tell, because it's all in capitals and it uses Roman numerals. This is clearly true. Fortran66 is a sort of standard, probably morphed in from Fortran 4. This is IBM. IBM really came up with Fortran, researchers at IBM. And there was Fortrans 1, 2, 3, and 4. They were sort of vaguely contemporary, and people weren't really happy with that. So people started to agree on a sort of standard at Fortran66. And I'm not sure it ever became a formal standard, but that was agreed on with the compilers. And we moved on a bit, and we came to Fortran77. We invented lowercase as well. And this was the perfection. This was the closest perfection as humans are permitted to come, really, in terms of Fortrans. And this actually became a standard. And that really helped it spread because the compiler vendors all basically adopted mostly that standard with a few bits and bobs added on. And that stayed like that for a very long time. Fortran77 wasn't changed. You know, the Fortran standards, people just said, it's fine. What's wrong with you? Why do you keep moaning? As other languages came along. And then something called modern Fortran happened. Around about 1990, people started talking about this new standard, and it was formalized in 95. And well, okay, it fixed a few problems that do exist with Fortran77. You know, I'm a realist. It's not a perfect language, nearly as close to perfection, I think I said. But it introduced a few very peculiar things. It didn't really fix all of the problems. It tried to be backwards compatible, which is perhaps a mistake with a language like this. And so it also paved the way for, well, other things where you're like, what's going on? And if you read the standards now, it's just, I mean, I don't know. And it's a shame. I don't know if Dominic's on the call, but if there are any modern Fortran enthusiasts in the audience, I apologize. I will occasionally bash it, but yes, I wouldn't say it's an improvement. It's a different thing. So how shall ye know it if you see it in the wilds? If you come across a piece of code, someone throws a piece of code at you, how are you going to know that this is Fortran77? Well, you might get lucky and see that first line there, which I have seen in code base. I actually pulled this out of a code base. I didn't just write it. Well, I remembered it and thought, ooh, I wonder if that's still around. And this is to help people know where they are on the screen, because Fortran is fixed format. Where you write stuff on the line matters. It matters a lot. And getting it wrong will screw things up horribly. You'll also notice that Fortran is always screaming because there's no lowercase. That hasn't been invented yet. So I will write everything in uppercase that's in Fortran77. So what is that first line trying to do? Well, you can see it, if you count, it has 72 columns. And that's because there are 72 columns plus a few extra bits at the end on a standard punched card. Fortran dates from punched cards. Early Fortran would have been written onto a punched card, fed into a hopper. You're looking at me like I'm making this up. Fed into a hopper, and then read by a machine which would parse it, compile it, maybe write it to a tape, if you were very lucky. Yeah. I mean, I've just missed it, but my supervisor certainly also remembers the days when you had to remember to put a weight on top of the hopper, the cards, because the enthusiastic card reading machine would occasionally blow your cards out all over the room. So yeah, running around with a deck of punched cards. And so there are 80 columns, and we reserve some of the last ones for extra bits and bobs. There are 72, and you don't go beyond that. The first column is the comment column. If it's got a C or I always get it wrong, an asterisk, then it's a comment, technically. I think some compilers said anything non-blank was a comment. So that line at the top, that's C, 1, 2, 3, 4, 5, that's a comment line because it begins with C. 2, 3, 4, and 5 are the label. So this is so that when you do a nice go-to statement, because everybody likes go-to, you need to be able to go to something, so you label your statements. It will be parsed as an integer. It can be space, space, 1, 1 for 11, or 1, 1, space, space for 11, or something like that. 1, space, 1, I don't think works. You can, I think, squeeze the label either to the comment side or to the other side. I can't remember now, but don't worry about it too much. You won't see that. The 6th column is probably the most exciting one, and this is the continuation character column. This tells you that this line is actually continuing the previous line. So rather than putting something like modern Fortran does at the end of a line to say, I'm continuing on to the next line, we say this line is a continuation of the previous line. And we do that by marking something non-blank in that column 6. And if you accidentally mess up your alignment, it's not a continuation line anymore, or it is by accident, right? So that's one cause of absolute horrific mistakes. The other fun thing is if you go beyond column 72, the compiler would just silently drop whatever you've put there. So if you maybe changed a variable name in your code to perhaps something more descriptive from I to ind, maybe you accidentally pushed it 2 columns further to the right, and now the compiler's just ignoring those last 2 columns and silently screwing things up. Okay, let's look at some more Fortran, because this is getting really good, right? Something you'll notice here is it's really squished as well, right? perhaps you say that j equals j minus square root line. Normally we would write that with spaces around it. We would put spaces everywhere to improve the readability. This looks really squished and cramped. Again, it's because it's got to fit on a punched card. If I start spreading out that way to the right, sorry for the people on the video, if I start spreading out and making my lines all verbose, I'm going to have another punched card. And that just is, I don't want to do that. Another thing you'll notice is, well, you may not notice, another thing that Fortran has is that the variable names are all 6 characters or less. So you can't even be particularly verbose with your variable names. No, no index of matrices ind or something like that. It's just mind. And you'll notice that, say, square root x, you can probably guess that's a function. We call functions with parentheses. But do thing I might well be an array, which is also used parentheses. Confusing? Well, that's because they hadn't invented square braces yet. They're not part of the Fortran accepted characters. You'll notice the continue line has a label. This is how you write a do loop. Right? There's no end do in Fortran77. You just say do label, and then you write it like that. It doesn't have to be a continue line. Continue doesn't do anything. It's a null statement. Modern compilers will actually moan at you if you put something other than continue. If you put an actual line there, it complains. What else have we got? I'm not really going to explain what these write star dot stars is. It's just too tiresome. What else? Yeah, I think that's what we can say about that. Oh yeah, and no indentation. Again, you don't want to risk going over your 72 columns. So this if block is not indented at all, nor is the do statement. That if block, by the way, that's a Fortran77 edition, which made code so much more readable compared to, say, Fortran66. This is what you had to do in Fortran66. If condition, go to somewhere. The next statement is the negative condition, then go somewhere else. Then you do the condition statement, and then you join up. Make sense? All right, so if delt is greater than 4, go to 90. So delt is high. Otherwise, carry on, delt is low, go to 99. Now, you might say, that's crazy, that's insane. It's the same thing. Your compiler is doing the same thing when it makes a block. It's just jumping over bits of code and then joining up at the bottom, right? This is slightly instructive that, sure, that's horrible to read, and it's quite horrible to write, but it's the same thing. You really haven't changed very much in the language. Okay, a bit of Fortran76 there. You still see that occasionally in codes, but hopefully not too much. So Fortran is strongly typed. It's a strongly typed language. Every variable has to be declared before you can use it. So here's an easy one for the audience to join in on. If I say ivar is ivar, whatever it is, times is equals 500, and I write it out, this compiles cleanly. What's it going to output? 500? No, on my computer, it output -9, whatever it is, 9, yeah, some gigantic negative integer. Because haha, it's a trick. This is an L. This is a 1. I tricked you. Okay, it's a daft trick, but it illustrates something rather interesting, which is that Fortran is just magicking these variables into existence. ivar1 and ivar2 both just got declared magically. And even when I used ivar1, and it hasn't been declared anywhere, Fortran was quite happy to just declare it for me. And so it then wrote out an uninitialized variable. So it's just garbage. This is because every program, every subunit has these lines at the beginning of it implicitly. And yeah, they are implicitly, and they are implicit statements. Real A to H, O to Z, and integer I to N basically means any variable that starts A to H or O to Z will automatically be real. And any variable that starts I to N will automatically be an integer. And that means you can just start using variables. You can just start coding. You don't have to waste time declaring variables. You can just get straight on with stuff. And people took advantage of this enormously. Partly because it saves on typing. It saves on punched cards. We don't have to waste time declaring all those boring variables. And partly because it's just a bit easier for the programmer. I'm going to start a loop. Do I? Oh, I have to go up to the top and declare I. No, I don't have to. I is an integer. Everyone knows I is an integer, right? By the way, you may have wondered why in your code, I'll bet you things that begin with I and maybe J, K, and L are always integers, right? This is why. Which came first, Fortran or? I don't know. You can override it, and you're supposed to override it these days. Implicit none turns that off. You now have to declare everything yourself. You can override it with more fun things. You can say all of my real variables are now real times 8s. All of my integers are integer times 8s. But if it begins with L, it's a logical variable. You can go crazy. You can change everything to integer. You can change everything to character, whatever you like. Go nuts. You will occasionally see things like this in code. So I'm just warning you. So what's this about? All right, so this is how you're supposed to do it. Yes, that's right. This is actually probably the least funny slide because this is actually what you're supposed to do. Implicit none. I'm declaring IJK index. I'm declaring some reals. I might say double precision. It's odd for a language that really likes being terse that double precision was the way you were supposed to say double precision. Real times 8, I think the times 8 stuff is actually in addition to the standard, but it's widely accepted. Fortran also has complex numbers as standard, which is quite nice, and it has logicals. Fortran77 is about the same time as C. C didn't have bools for years and years. So yay, Fortran's better. It has character arrays, which are fixed length. Again, C just had sort of the airy-fairy, pointery things, which led to the chaos of the 90s, the 2000s, as string overruns in C string overruns just dominated the world with bugs and mistakes. If we'd had Fortran doing that, it wouldn't have happened because, well, it would. But a character array in Fortran is space padded. So if you write hello into your 13-character array, you'll get hello and then a bunch of spaces at the end of it. Cool. So, common nonsense. So, okay, that's fine. That's variables inside a routine. What about global variables? Every good language should have global variables because they're really good. So Fortran has something called common. You declare common with a name, so consts is the name of this common block. And wherever you declare that in a program and perhaps in a different file, in a subroutine, in a whole bunch of different files, they are the same variable. Have I got not? No. And the idea would be that you would have common consts C10, which declares an array of C, which is real, of course. And then later on, I've actually broken it out. I've gone A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I don't know why I did that straight away. I think I was supposed to just show you how to use common. But anyway, so the idea is common is globals. Anything that has this common line in it will have access to this global variable, and it's all the same variable. But you can play silly games. So that's an array declared in the program. In the subroutine, it's 10 separate real values. That still works. That compiles quite cleanly, and it will run, and it will do exactly what you expect. You can do something like that. You can have an array of 10, and then an array of 9, and P on the end. And you might sometimes see something like that, where someone's got maybe an array of constants, and they just are actually only interested in the last one. They don't have to keep remembering that it's C10, so they'll give it a name. P is not a very good name, but they might call it, I don't know, C light or something like that for the speed of light, right? Just to help them remember. So, okay, that works. You can even do stupid things like this. You can have your common consts, which is 10 real values. And later on in a subroutine, you can say it's 8 real values of one complex number. Because one complex number is 2 reals. That compiles quite cleanly, and it even outputs exactly what you expect, which is 1 and 5, right? The 5 coming from here. That's C10. And did I go into further? No, I didn't. You can even, and I will demonstrate this with subroutines, you can even basically just alias completely arbitrary pieces of memory together this way. And that was done. One of the reasons that people did this sort of thing with common is that Fortran lacks one very important feature in Fortran77. It lacks dynamic memory allocation. And so saying common big number would basically put a big chunk of memory on the stack, and you could then chop it up and hand it into your subroutines in various different ways as you go along. I'll demonstrate a different way of doing that later. So modern Fortran tried to solve this problem of the common block by saying you can't have common blocks anymore. And so when people then migrated to modern Fortran, they said, oh, modules, that's what we're supposed to do. And they made a module, maybe mod constants, and they put their variables in it and they declared them. You know, that's how you declare pi. That's the only way to declare pi. And don't. Yeah, so lots and lots of constants in the module. Brilliant, right? And then they'd say, wherever that common block had existed, they'd just say use mod constants. And the problem with that is, if this is in some other file, if I'm editing this file and I see it using pi, I have no idea where pi came from. I've got to search through all of the modules being used, which might be dozens, to find out where pi came from, or where whatever it is that's been brought in this module. At least with the common block, I could see it at the top of the file and know that it was a common block. This is worse. They actually made it worse. Now, you're not supposed to do it this way, but they left it so that you could. And people inevitably will take the easy route. Good. What about subroutines and functions? Subroutines take arguments and don't return anything, and you end a subroutine with the return statement. Functions take arguments and must return something, and you can't use return in a function. So, I thought it was funny. So this is just a function. The function name is typed just like a variable is in Fortran. So I can explicitly spell it out, jfunc, or I could leave that off because, of course, jfunc begins with j, and therefore it will return an integer. But that isn't very exciting. You just assign to this name, which gets magically added to your scope inside the function. A subroutine, sorry, you call with the call statement. I presume because they couldn't think of a good way of dealing with the fact that it doesn't return anything. And so you can actually call a subroutine that has no arguments in two different ways. You can just call it munged, or you can call it munged open close empty parens. You can also declare it with empty parens as well. But we want to pass arguments to subroutines, all right, and functions as well. This all now applies to functions. So, okay, that's fairly simple. We declare some argument inside the subroutine. We say what it is. We write it out. That will write out 1. Not very exciting. Hang on, I've lost a load. No, okay. And you can also make a mistake and put too many arguments in your call, and that will compile. This compiles quite happily as two separate files, I have to say. If you compile it as one file, the compiler will notice. I think it's only modern compilers notice. But if you compile it as two separate files and link it together, not the slightest warning at all. And so you'll notice I'm calling short sub with 3 arguments. Yeah, I realized that later, sorry. Short sub, it's 6 characters. I'm limited here. Short sub with 3 values and getting 2 back in short sub. And you can do the opposite. You can call it, say, with 1 and pull up 2. And this is instructive. We're discussing something like this at lunch. What is going on here? Why is it that this is working? And it's because the compiler just compiles. The Fortran compiler has no idea what short sub is. It just assumes you're going to provide it later. Right? It's not like C where you have to pre-declare it. It's not like modern Fortran where you have to define it in a module file. F77 just says, I guess you know what you're doing. I later declare and define short sub in some other file perhaps. Then it's the linker's job to stick them together, but the linker has no way of checking any of this. The normal linker just goes, ooh. It sees short sub being called, it sees short sub being defined, and it sticks them together. So what's actually happening inside the short sub routine or function is, well, when you call something, you push arguments down onto the stack. So in this, the stack, if you don't know what the stack is, too bad. Basically, like a stack of plates. You push an argument down. So here I'm pushing 3 arguments down, and I'm pulling up 2. That's actually okay. Nothing, I think, terrible will happen there, probably. This one is obviously bad because I'm pushing 1 argument down, but I'm pulling 2 up. Well, what's the second one? I don't know. Could be anything. It might be a memory override. I might read memory I'm not supposed to be reading. Stack underflow. Who knows? So that actually runs on my computer and produces garbage, but it could segfault. It could crash. But you won't know until you run it. It's a runtime error in Fortran. Oops. What else can you do with subroutines? You can have lots of fun. So we saw that you could have a program calling munged, and munged was declared, as we saw before. But now in munged, I've got dummy I, which begins with a D, so it must be a real value, and I've spelled that out for you just in case. So what does this do? I can't remember what this does. It produces some absolute nonsense number. That's right. Because I'm pushing whatever that is, 1 billion down onto the stack as my argument to munged, and then I'm popping it quite happily up. The subroutine munged is saying, yep, here's my argument. It's a real argument. I will treat it as a real number. And whatever that integer looks like as a real number, 2.31 blah, 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 times 10 to the minus 35, that's what it is as a real number. It's the bit patterns. We're now actually getting down to the actual representation in memory of this integer. It's not very interesting. It's not casting. I haven't cast it. I'm actually looking at the memory here. Why would you want to do that? I have no idea. I can call it with a logical. So I can call this thing that's expecting a real number with a logical value. That's how you do logicals in Fortran. I think that's quite cool. And again, you get some number because a logical internally is going to be some bit pattern in a field. It's just ones, I think. Again, that's not particularly useful. It's not even casting a logical to a real, where maybe that would be 1 or something like that. But this is paving the way to other things. So we can do something like this. This might take a little explaining. I didn't write any notes this. So here I'm saying, let's call a subroutine with 4 arguments. And there's an integer, real, complex, and a 4-byte character. That's what character times 4 is. And I'm calling it with 1 single integer array. So this is just an array of 1-byte integers, 20 long. And I'm just chopping that up and handing it in to this subroutine. Now this actually works fine. This will compile and this will work. This will do what you expect inside this subroutine. If you try and use this array out here, you're just going to be reading garbage because it's all now integers and you've put reals and complex numbers and characters in there. But in here, this all works fine. Which is interesting because if I could have some way of getting an array of lots and lots of memory, lots and lots of integers, I could then start chopping it up manually. A bit annoying. It says manual memory management. So now I can basically do something like this. I can say, here is a subroutine called memman, which is going to work out offsets. Now, int size is some function which just says, if you have max-mat integers, it returns how many real numbers are needed to cover that many integers. Right? So if the real number would occupy 16 bytes, because it's let's say 8 bytes and it's a double precision number, then that's probably 2 integers, right? And we just have to assume that we've coded int size cleverly, probably in C, to work out exactly how to do that. But we can then work out offsets into some memory array, which of course is real because it begins with M. And then when we call doCalc with these offsets into this memory array, we can treat it as integers and reals or whatever it might be. We're doing memory management. I said we've got pointers. These are basically pointers, right? And if all you need, therefore, is the one thing that Fortran77 was missing to make it great was dynamic memory allocation. But you can call C routines from Fortran. You can call malloc from Fortran relatively easily, these days quite easily. And you can therefore allocate a big chunk of memory using cmalloc, chop it up in your Fortran program, and have dynamic memory management. Now you're doing it all yourself. You screw up, bang, it explodes and you die. Or more likely, you overwrite maybe 1 byte of your answer and you don't notice until thousands of iterations later. That's the sort of thing that happens. But this is not uncommon in codes, because running out of memory in something that doesn't have dynamic memory is a problem, right? You can't just keep putting everything on the stack. And so C was there. People looked at C and said, this looks horrible, but oh, it does have malloc. They took just malloc from C, a few bits to make sure they could call malloc correctly, and then they did this. I have seen this sort of thing. This is largely taken from the code with the names changed to protect the guilty. What else? What we got? No, we did quite well. So now let's get into the really bizarre stuff, because that's all been pretty boring. So the standard, it has this thing called equivalence. Equivalence is one of those things where you think, yeah, that looks fun. This example where I have A, B, and C, which are character arrays, and the times just means how many bytes they are long. So A is 4 characters or 4 bytes, B is 4 characters or 4 bytes, and C is an array of 3 bytes, the 2 times 3 bytes. So it's an array of length 2, and each element of the array is 3 characters, 3 bytes. If you do that equivalence statement, you say, let's put C1 onto A and C2 onto B, then A and B are moved so that they overlap. And then C occupies like that. Now, I cannot think of any reason why you'd want to do that. This is from the standard. This is from the Fortran77 standard. This is the example of why you might use equivalence. What? I do not understand that at all, why I would want to do that. I can think of reasons why I might want to use equivalence. It's kind of like a union. I've got some allocated space, and I sometimes want to use it as an integer, IFP, or a real, and so I equivalence the two together, so that I've missed out the integer IFP part. So I would say they occupy the same memory location, and then I might have some parser. If I was excited enough to write a parser in Fortran, which people have done, I might be where I'm parsing things, and I don't know what type they're supposed to be yet, but I've got the value stored somewhere. That sort of thing, maybe, but we're getting, I'm getting a bit desperate here. I don't know. Things which I have to show you because it's fun. This is technically still in Fortran77, but it is sort of deprecated. It's really Fortran66. This is called an arithmetic if. You say if expression, and it has to be some sort of arithmetic expression, so a real or an integer or a complex. Complex? I don't know. And then there's 3 numbers. If the expression is negative, it will go to the first number. If it's 0, it will go to the second number. And if it's positive, it will go to the third number. This is basically like if then else, but for an arithmetic expression. And of course, you still have to put these guard go-tos to get out of the way. So you've still got this horrible spaghetti mess going on here. I think that's quite nice. What do we got here? Oh, computed go-to. Oh, I love a good computed go-to. Basically, you have some integer I, and if it's between 1 and 3, then we will go to the value in that computed go-to list that corresponds to the number I. So if it's 1, we'll go to 10. If it's 2, we'll go to 20. If it's 3, we'll go to 30. And if it's not, we will just fall through the go-to completely. This is a jump table. This is, again, something that is actually low down, quite important and useful, but you don't really want to see it in your supposedly high-level language. But yeah, computed go-to. You will occasionally see those as well, although they're very rare. And yeah, the last thing, rugose and squamous. There's one thing I found in the standard which I've never seen in the wild. It's called entry. You basically declare a subroutine. You have a return statement in your subroutine. Well, I think you don't have to, but you have a return statement in your subroutine. And then you say entry with a new name and some new variables, and you just carry on. And the idea is you can call the subroutine with either of the names, and you will enter it at that point. Now, I don't think you have to, I was going to say, all the examples I've ever seen have had the return statement because it really makes no sense without the return statement, but you don't. Well, then we've got some excellent questions coming up. But yeah, I have not thought of a reason for why you could possibly want to use this. All the examples I've seen have been totally confected. So fascinating. I would love to know why we might want to do entry. So you hopefully won't ever see anything like that. And that, I think, is the last slide. So, which isn't too bad. So, yeah, okay, we've had a giggle. We've laughed at Fortran. We've laughed at some of its silliness. Hopefully, you've been slightly inoculated so that if you do come across this in the future, you will not just immediately, go do lally, and you will go, oh, yes, I know this. It's Fortran, RM-FR. But at the same time, I think it's interesting, and this is partly, I haven't put any slides here because this was an idea that came to me while we were eating lunch, which is that this is an early language. These are the sort of languages that were coming along to replace assembler or replace really, really crunchy, tiny languages that looked like assembler. C is being born at the same time as Fortran77, and C has been described as glorified assembler, basically. And they are the way they are because they are very directly mimicking the way that the machine is and works and is laid out. And I think that if you understand something like F77, or maybe C, okay, that might be better. But either of these two, you're going to get a very good idea of what is actually going on at the real base level. When I say a complex number is obviously this many bytes long, I can see some of you looking a bit baffled. To me, it's perfectly obvious because I've had to actually step through those bytes to see what is going on. Because one of my architectures has swapped the order of the endianness or something like that. Right? It matters at this level. Most of the modern languages just abstract all that away from you. And that's good. But knowing this stuff, I think, allows you to both optimize and understand what's going on in your high-level languages. And there is still a reason why a lot of these Fortran77 codes still exist, is because when compiled, they go really fast, just like C codes do. Because it just crunches down to basic stuff, and it goes like the clappers. So I come to praise it, not to bury it. I think there is maybe a lot of life in it, but some sort of undead shambling, which we should respect in this particular time of the year. And I think I can take questions. Yeah.
I'll give you a use case for that example.
Yes.
You take the return out and replace it by A equals I, B equals J, C equals K, then you have two versions of that subroutine, one which takes integers and one which takes reals, and they do the same thing.
Yeah.
The other question I had, does Fortran77 actually require a stack? I know old Fortran did. 77 does. Old Fortran, they used to start the arguments at the beginning of the subroutine.
Yes. And
if you put in too many arguments, you overwrote your code.
Yeah. I'm trying to remember from the standards. No, I don't think it mentions a stack. I'm trying to remember the phrase it uses for the processor unit or something like that.
I know that the Fortran66 explicitly didn't require a stack.
Yeah. No, I think it's an implementation detail. Yeah.
But that matters a lot.
Oh, sure.
Different numbers of arguments.
No, granted, yeah, I am kind of talking about modern architectures, which normally will implement this in the C-like runtime. So
yeah, the original Fortran was designed for machines that didn't have stacks. So you couldn't choose a stack.
Yeah. There you go. Oh, so what do I do this? All right. Okay, Chris, sorry, I should have seen that when you did it. Yes, that was deliberately set there as a trap. And I'm sorry, Chris, I didn't get there. Yeah, what's up with you? Okay. Logic was supposed to be the same size as integers in the specs. It's a bit superficial, as are balls in C. I'm not sure it specifies in the standard what size a logical is. I think you might be able to do, no, I don't think you can do logical times 1. I don't know about that, Ben. You might be right. You're probably right. Explain a few of the things you've seen in modern Fortran. Yeah, I think that's one of the ideas is you will see modern Fortran and you will sometimes ask yourself, how the hell did this get written? And why is it calling itself modern Fortran? And the answer is it isn't. It's just ported across from F77 with the minimum of effort. And these things, you'll suddenly go, oh, that's why that's there. Anything else from the room? So Ben says, later specs say that logical times X has to use the same size as integer times X, but don't specify size. Maybe not in F77. Yeah, I think the times X is actually just marginally past F77 standard. I think it's between that and 90. Thanks, Ben. Yeah. So you can have arbitrary sized logicals to hold your true or false value. Cool.
You have any recommendations for writing new code? And we need to make C++ or Fortran or something else.
So I've been asked, do I have any recommendations for people writing new code? Would I recommend C++, Fortran, or something else? I think something else. I know some people do like modern Fortran as a sort of teaching language. I'm not a fan. I think it hides some important things, but also is quite bare bones in others, because it is this weird fusion of trying to be backwards compatible. C++, I wouldn't really wish that as a starting language on anyone. My go-to is Python, which is just a nice, friendly language, and you can do a hell of a lot with it. And if you do need to go to something else for performance, then the syntax is not dissimilar to something like C or C++, which might well be what you'll end up doing. But if you're learning to program, yeah, anything really, anything that you feel comfortable with, or if you have a particular problem which perhaps already lends itself to a language or has examples in a language, go for it. I mean, I hear Julia's really fast. We're all learning Julia, so that's a big job. Then if you're learning code and you find it's too hard, just change, just go to something else. It's probably the language, not the
Speed.
speed. Is 90% of the time, speed is not the issue. The efficiency of a code is how efficient it is at making programmers put code into it, or it's the efficiency is the performance is the last thing you care about, right? So get it working, and by the time you've finished getting it working, you may well have worked out how to make it go fast. That might be rewriting it, it might be changing parts of it. But just getting it working, and therefore a language which is easy to get something working in. So interpreted, friendly, Python. Your time is the most important thing. Computer time is cheap. Ish.
In that case, thank you very much. That was very entertaining. Everyone's minds are slightly blown. But I would say, yeah, thank you very much, Simon.